Okay, so trying to tie together, all the different things in linear algebra, or at least some of the different things. So we started off by looking at systems of equations, right? And so like your system could look something like a11 x1 plus blah 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 plus a1 uh, n xn equal to some constant. Let's call it b1. And then, you could have m equations. And then you would have, so this would be A1, AM1, X1. And then you're also going to have N unknowns, right? So that's going to be A1N, XN, BM, right? And when we studied this in the past, there's a geometric significance. So if you were looking at the R2 situation, you know, here's your axes or whatever. You could have one line that goes like this and another line that goes like that, so they intersect at a point, right? Or you could have sort of two lines in parallel, right? So this is one solution. This was no solutions. And then you could actually have two lines that sort of like lived right on top of each other, and that would give you sort of an infinite number of solutions, right? So this was the first way that we sort of looked at this idea was systems of equations. And you could bump it up to the R3 case and you could still visualize things, right? So you have, the intersection of two planes. And when you have that, it's sort of like, the intersection could be like an object, like a line, and this is like an infinite number of solutions. Okay. So that's how the course kind of began, right? And then we, for some reason, said, you know what? Let's extract out the coefficient matrix A. This is the coefficient matrix. And then let's rip out all of the variables. And let's call all of the variables X, right? So A is m by n. X was n by 1. And then let's, extract out all the constants up here. And that's going to be a m by 1 matrix, right? So this is still the same point of view as what we had before, that just kind of changed the way it looks by introducing a matrix. And, so maybe I should say, oh, this is a matrix. This is a vector. It's not just any vector. This is a Rn vector because it's n by 1. And this is also a vector. This is a Rm vector, right? So that's just a direct consequence of this systems of linear equations, right? All right, cool. Well, lately, what have we been doing? Lately, we've been taking this same type of object and we've been thinking of it like this. Here's a vector space. Call it Rn. It's a vector space. Okay. And then here's another vector space. Let's call it a vector space. We're calling this guy Rm. And then we can think of the same situation that we just described above, but we can think of it as a linear transformation. And what is this linear transformation? It's multiplication by A on the left, right? So what happens is you start off with some vector, let's call it x. Then you apply the linear transformation to it, and then you get something that lives in Rm. That's called Ax, right? And that's the image of x under this linear transformation. And then we call this image B, right? Okay, so all of a sudden we switched from solving a linear system to thinking about it as linear transformations. And when we think of it as a linear transformation, what does solving this linear system mean? So from the systems of linear equations point of view, what does solving, or how does, let me say, how does this situation translate to the linear transformation point of view, right? And the way that you can think of this is you can think of the B. This is a specific vector. This vector is in the image. So this vector is in the image of our linear transformation T, where T is multiplication by A on the left by A, okay? So really, when we're solving this linear system, we're saying, oh, okay, you've got something in the image. So this is an RM. You got something, some specific vector in the image, and you're really asking yourself, hey, this must have come from some other vector um, in Rn, right? In other words, this came from somewhere. And the question is, where did it come from, right? So solving uh, ax equal to b is really saying what is the pre-image of b in Rn, right? Okay. And this actually relates to the idea of a linear combination, right? Because, you know, take a look. When I look at ax, right, how can we think of ax? Well, I can really think of this as the columns of A. So we got first column. How many columns do we have? We have n columns, right? Because the transformation goes from Rn to Rm. So these are, you can think of these as column vectors like this, that's what you're regarding as A. And then you also know that we got x1 through xn like this, right? And we know how to do matrix multiplication. So how does matrix multiplication work? You sort of multiply the, you multiply the, you multiply the first column by x1, plus you get the second column, C2, you multiply that by x2, and so on and so forth. Plus xn is multiplied by cn like this, right? Okay, that's really what ax is. And if you look at exactly what we just wrote here, basically we are taking linear combinations of the columns of A. Okay. So what is this trying to say? So we're basically saying, okay, I have AX equal to B, right? What is that saying? Well, that's really saying, you know what? You got X1. In fact, you know what? Let me just copy, cut and paste this. That's saying, you know what? We basically got this guy right here. Copy this guy. This is supposed to equal to that vector B. So this has a solution, you know, uh, we are, you know, let me say like this. So we are trying to write B as a linear combination of column vectors of A. Now, we don't know a lot about these column vectors, right? So we know that these column vectors, they live inside Rm. They're m dimensional. M is in mummy. Okay, so we know that, but we don't know, don't know if they're independent. They're independent. We don't really know that much about them. We know that they come from Rm, right? So if you think about it, um, what we're trying to say is that all right, I guess B is in the image if and only if I can write B as a linear combination of the column vectors. So this is great for us, right? So this kind of ties it in to, I guess this tries to tie in the idea of solving linear systems with um, with linear transformations. Okay. Now, what else do we know? You know what? Maybe I'll stop this. I'll stop this video here. So let's just end it here if I can. I gotta figure out how to stop this.